Okay, yeah, so hi everyone. Thanks for coming. So if you remember last time we talked about spectral graph theory and we talked about free union of perfect matching and zigzag, which hopefully we'll get back to at some point. But I promised you a detour to free probability theory and that's today. So today is going to feel like a lecture, like definition and proof and stuff. So I cheated and I actually am going to copy you and do like that. So as I told you, free probability theory is the one, if you don't know about it, then it's the one other probability theory you probably don't know about because there are only two, which is kind of amazing. And you'll see today, freeness is going to be our new notion of independence. We are going to prove a central limit theorem in free probability theory. And actually also we are going to prove a central limit theorem, the usual central limit theorem in classical probability, but probably in a different way than you saw it, like in a combinatorial way. And then we are going to kind of delve deeper, but I can't really say what's here until we are going to do all of that. So if you think about it for a second, then classical independence, you may think of like tensor product or stuff, but in terms of moments, classical independence is like an algorithm or a prescription or a formula for computing joint moments like this above than the marginal moments like that. Right? Usually, if you don't know anything about A and B, you can't compute this thing. You need extra information. But saying that they are independent is essentially saying this, right? It's saying that there is a formula for computing this mixed moment from these marginals. And freeness is going to be, turns out, and you can formalize that, the only other way of doing that. There is only one other consistent way, like if you put up some axioms which you all believe in, then there are going to be two formulas. This one, which is kind of boring and we know it. It uses the commutativity very heavily. And another one. And the other one is what's the underlying thing about free probability theory. Okay. I'm not going to prove that, but... So let's set the ground for studying what is this new notion of... it's a fairly new notion from like 85 or something of probability theory. So the technical term is a non-commutative probability space, NCPS. So it's a tuple. Here is where the random variables live. So here in this, unital C algebra just means that, it's a ring and also a vector space over C. So you can multiply, sometimes invert, add, and multiply also by scalars, like matrices. So this is where your random variables live. So here you have like, you have your A's and, oh, that's bad. You have your A's and that's also not so good. Yeah, you have your A's and B's and maybe A inverse and maybe A plus B and B squared and so forth. All of these are random variables sitting here. And phi is going to be the measurement. It's going to be, I think of it as expectation, but phi of a random variable, it's a number. It's going to be a complex valued number, and you will think of it as expectation in some sense. You will see an example in a second. So that phi is a unital linear functional. Unital just means it sends 1 to 1. And the fact that this is a unital C algebra means you have a 1 there. Okay? So there is a unit. Okay, well, I'm going to also assume, even though we are not going to see it, so I'm not going to lie, that phi is what's called tracial, like the trace. It's a quick form of commutative in a sense. So phi of AB is phi of BA. At the presence of some C, it's not the case. But phi of AB, you can always cyclic take the last one and put it back to the first one. Right, so don't worry about that, but some things I'll say are just not true, and I don't say that, so I don't want to lie. So there are two examples, one that I care about, and the other which is very relevant to this workshop, so I decided to put it. So the example that we will care about are n by n like complex valued matrices. And then phi is going to be, I told you it's like a measurement. So how do you going to measure your random variables or matrices? They don't have to be like random matrices, they're just matrices. This is the normalized trace. Right, so in what sense this is like an expectation? I mean, A is fixed, so I call it a random variable, but it's just a matrix. So in what sense I think of this phi as an expectation? Because the normalized trace, you can write it like that, but you can also write it like that, which is just essentially expectation over the eigenvalues of A. I lambda is our notation for the ith eigenvalue in some order, I don't care. So you can think of it as the matrix encodes a distribution, which is the uniform distribution respecting multiplicities of the eigenvalues of the matrix. Another example, which I hope I'm not going to open a rabbit hole now, is when you take a group algebra. We saw quite a lot of those, actually twice or 3 times so far, so I don't need to define it. That's a good algebra of this group G. And in this case, the right notion of an expectation is looking what happens to what's the coefficient of the identity element. So now we typically also equip our non-commutative probability space with more information. Sometimes you put a norm. I'll not use a norm, but I'll use this thing. So like in matrices, you have this star operation, the conjugate, and it's this involution that is. I forgot the name for that, but A, B star is A star, B star, A star. It respects addition. It's nice, plays nicely with the ring. And also there is this kind of requirement, making sure you are not degenerate, which tells you that if you are kind of positive in a sense, then phi captures that, phi is positive. So phi of A star A is like non-negative, otherwise you could get otherwise you need to quotient by something, so this won't happen. And you also want to kind of assume that A is 0, so this is 0 only if and only if A is 0, so that you will measure things rightly. Don't worry about that, but that's just something that kind of give you a taste of how the abstraction looks like. Right, now you can conjugate and talk about PSDs and stuff. Actually, that's good. So with that abstraction, you can abstract what you like. Like you can look at properties or some of the random variables. For example, self-adjoint, which in matrices means they have real valued spectrum, which is also the case here if you define spectrum correctly. And unitaries, right? So a unitary as a matrix satisfies this thing, 1B, the identity. Normality algebraically can be expressed like that, even though in my mind, I don't know how you think about normality, but I think of it has a orthonormal basis of eigenvectors. Right, initial probability is just going to be like the conjugation if you're a complex valued variable. And by the way, what's the conjugate here? Like of this of G, like G is one of these elements, right? So
G inverse.
G inverse, right, good, yeah. So conjugate is like what it should be all the time. It's like it works. C you would conjugate and the group you inverse, right? Yeah, good. I think it's written just in a second. But anyhow, using that, and I think it's kind of nice. You look at proofs that you always prove. You see you don't use anything other than those like axioms or properties. So you can prove Cauchy-Schwarz, which will look like that.
Yeah, you just need to show that it's an inner product. Right?
Exactly. So you see that you get an inner product, therefore a normed space, and you can complete it, and you can do all kind of stuff like that, which we are not going to do, but it's a whole new abstract world. This is the example that I was talking about, but yeah, you're right. Those alphas you need to conjugate, and G should invert. And okay, so that's what we do in when you do free probability, you work with moments. That's what you do. Like phi encodes the moments, the algebra encodes the relation between the random variables. It's like in groups, there are relations, and in like A, B, A inverse, B inverse could be 1 or whatever. So you can encode that using the algebra in a more general setting. But you work with moments, and so it doesn't feel like a probability theory at all. It looks like an algebra theory. But it is also a little bit of probability theory because, at least in some cases, so there is this notion of an analytic distribution. At some point, you want to kind of cash out for moments and talk about measures. So if you have an element, little a, which is normal, namely it commutes with its conjugate, then sometimes, for example, whenever a nice thing happens, you can also associate an analytic, like a standard, Lebesgue measure or distribution, don't worry about those things, with that element, which encodes the moments. And sometimes the moments are just weird and there is no distribution, but sometimes there is. Namely, sometimes you can find a measure mu. And again, if you don't know what d mu z is as Borel, just think of it as mu z dz and everything's fine, just a density measure. That encodes the moment. So in what sense? So for any k and l that you will plug in here, and note that I'm only looking at these monomials because I can conjugate a and a conjugate. I can commute a and a conjugate. Then that moment is captured by the corresponding, when you integrate against the measure, the right function. And I needed normality for that because otherwise, this always kind of commute z and z conjugate, but these may not, and then it doesn't make sense. to require for non-normal elements to have an analytic distribution. So for a normal element, when there is a distribution mu that integrating against this expression, you get that expression for any KNL, it turns out it's unique, and it's called the analytic distribution of A. It has a longer name, but I call it like that for now. Right, so you construct your algebra, you set moments sometimes you do it like that, sometimes you do it in the other way, and then sometimes you care about what's the analytic distribution of that element, or does it exist at all. Right. I will see an example just now. So this is going to be a special kind of element in a potential non-commutative probability space. So let's say we'll call an element U a random variable. Are unitary, first of all, it's unitary, which we call means that it satisfies that. And also, except for the first moment, except for phi of u to the 0, which is 1 kind of by definition, you want all moments to be, because phi is unitary, it sends 1 to 1, you want all moments to 0, to vanish. Okay, that's a weird requirement. It's like a very kind of, this kind of moment behavior. At 0, you're 1, otherwise you're 0. But that actually does correspond to a very natural element. It's essentially a kind of a rotation, in a sense. I call it Haar unitary for good reason, and we'll see it tomorrow more explicitly. But I just want to say that the corresponding analytic distribution here is, you look at the complex plane, and it's the uniform distribution over this unit circle in the complex plane. So that's the corresponding, it's a nice exercise to do. That's the corresponding analytic distribution. Kind of what you expect if you don't do the calculation.
Well, why is it
No, it's like a complex, so it's one day. Right. Yeah. We started like that, but that's one dimension. That's like weird, like reals. Right. So that's a nice exercise to do. Actually, it's very easy. You just look for what distribution satisfies all the moments equalities, and you get that. But now that we set the stage at least, we have the random variables in A, we have the measurement phi. Now I can talk about what is freeness. When are two elements, for example, or more, are free from each other, like independent, but in the new sense. And actually, the definition that, if I want to give a straightforward, like right away definition without motivating things, it's kind of underwhelming. It looks like a very unnatural definition. And yet here we are, and I'm going to do it. But we're going to see it's just the wrong definition. It's a right definition, but it's expressed in moments where it should be expressed in other means called cumulants. But let's stay with that and just. Don't worry about if you feel that this is a weird definition. Again, you have a non-commutative probability space, and you take two elements, and you're going to say that they are free and think independent. If they are, first of all, centered, you just center them. That's fine, right? You don't care about that much. By center, I mean subtract phi of A from A. It makes sense to do that because, that's technically a number. You should multiply by the unit of the ring, but okay. Minus phi of A identity. So they should be centered and alternating. So what I'm saying, say you have A and B which are free and they are centered, then every alternating mixed moments of them vanish. So what do I mean? So we are going to use this notation for centering. So A bar or whatever bar is A or whatever that is minus phi of that thing, that's centered. And I want, I have an infinite number of constraints here. I want that phi of A bar, B bar is 0. And I want that phi of, every element from A bar, every element from B bar, and so forth. Every polynomial that you'll put here in B. Here, because I'm talking about just about A and B, a polynomial in B is just like a power of B. Generally speaking, I can talk about A, which is free from B and C. And then you have a more interesting polynomial in B and C, and then you don't need to worry about the coefficient of these polynomials in B and C. Like maybe you have BC, BB, and plus BCA. Right, so what you really mean is that, so you want A star, and 1, the algebra generated by those, when you centered each of these elements and take alternating terms like that, that should be 0. You don't look at this. Right, exactly. So this is not that. I mean, sometimes it is, when the variance is 0 or something, or I don't know. But they all need to be 0, right? So so this has to be 0.
Yeah, when they had to outside. Okay, that's different.
Right. So is it clear? So this is kind of important. Like it's the definition here. So what I'm saying is that if you take any power of A and center it, and multiply it by any power of B and center it, and do that alternatingly as many times as you wish, like finitely many, phi of that should be 0.
And where are you allowed to use stars?
Yes, and you are allowed to use stars. I kind of try to hide it, but also stars.
But not A and then A star.
That's in the same thing. So if you have A star, you do like this. Yeah, because it's in the same algebra. It's like the algebra generator. So we'll see exactly how it opens up, and like that's the usual probability. That's like how we Huslanu. How do we? So let's see. Let's play with this. Let's play with this definition. It will be clearer because of these two examples. So let's say I have an A and a B, and okay, just to make sure, if all of these infinitely many constraints happen, when I say that the A and B are free, and if we have also the conjugates, then A star is free from B star, for example. But don't worry about that. So let's take an example. Let's take one A and one B, center each of them like that, and take their product. So I'm looking at, this is what I called A bar before, but I want to be more explicit. So this is A minus phi of A, B minus phi of B, and I'm taking their product. And if they are free, and I'm kind of assuming they are free, and I try to see what I can get from that, then I know that this thing is 0. But now on the other hand, I can just open things up within phi, and because phi is additive, you can open it up. So with inside of phi, you will have AB because of these two, the usual thing. You should remember non-commutativity sometimes, but the usual thing. And then A phi of B and so forth, you have all of these 4 expressions sitting inside phi. And then if you kind of apply phi to each of them, and remember that this is just a complex number that goes outside, for example, and stuff like that, then you'll get something that's kind of not very surprising. You get that, you get 1 phi of AB because of that, and minus 2 plus 1 phi of A phi of B, if you'll see it from here. Because when you apply phi to this thing, you get phi of A phi of B, because the phi of B goes outside. Right, because phi of A phi of B, this thing just goes like that because it's a number. So it's phi of A phi of B, so you got 2 minuses of that plus 1 of that, so you get phi of AB minus phi of A phi of B. And that's 0, so that just means what we always knew. That phi of AB is phi of A phi of B. Not great, not a great start. If you'll do it for what we like to call ABBA, because it's easier to, you live once, like this, and open this up, you get again something very boring. You get the usual thing, what you expect. It will be phi of A squared times phi of B. It's like as if you commuted A. Actually, it kind of follows by the tracial property and what I just said, but never mind. It holds even if you are not tracial. But more interesting, what happens is and that's where things starting to get interesting. If you take a bab, when you open this up, and you see what it kind of isolate phi of AB, which is not normal, not centered like that. When you get a sum of 3 expressions, like you get phi of A squared, like the variance because it's normalized, times phi of B squared. So it's not normalized, but it's phi of A squared, it's like the variance essentially, times phi of B squared, and then you have the other expression because it has to be symmetric, it only goes so far how it can be. And then you subtract twice, like 2 powers of the phi of A and phi of B. And if you compare it to the classical case, you actually only have the one thing that doesn't appear here. Right? You don't have a phi of A squared, phi of B squared. You have phi of A squared, phi of B squared. You don't have any of those sitting here. In the classical, because this just goes like here, and the A and B are independent, so it's phi of A squared, phi of B squared. Classical, I mean in commuting random variables. So the classical just means that this is I can commute, and then independence, classical, I mean independence. Yeah, independence is this. Okay, so first of all, you can ask, like it or not, why haven't I seen it before? I don't know. It's like, what is it related to which I'm not doing? So there are 2 reasons, and together they kind of filter out almost everyone. So one is that commuting random variables are never free, unless one of them is constant and it's not fair. Constants are just like moving out of the fees. So if you are commuting random variables, you will never be free. You don't see freeness. It doesn't appear in commuting random variables, which is what we usually do. And secondly, even if you do work with non-commuting random variables, and you do, like matrices, then you never see them in finite dimension. It's an infinite dimensional phenomenon. You can prove that there is no finiteness. Freeness cannot be materialized in finite dimensional vector spaces, like operators.
So over the matrices, we don't have freeness.
You don't have freeness. We have like what's called asymptotic freeness, but we don't have freeness per se. Right, so I mean, this rules like most of our life experiences. But actually in this crowd, it's not, right? I mean, if you have two D by D matrices, they can never be free from one another unless one of them is a multiple of the identity. Yeah, good, that's important. So I reiterated again the fact that, you can say, well, I don't look at it because of these two reasons, or I don't look at it because it's not interesting. Maybe that's another reason. So maybe, but it turns out, as I said, it's the only other, you can put like 4 axioms and ask what are the possible ways of computing mixed moments from joint moments in a natural way, and you'll get 2 outputs, this and usual probability. So that's that remark. So the fact that we like to study non-commuting versus commuting, it's more general. It's not that. It's something inherent, not something about what we are interested in. Yeah, so freeness is an assumption on, so if you have 2 variables A and B, just, abstract element in the non-commutative probability space, if it holds that whenever you take, A to the 4 and normalize, the center, and multiply by B cube and normalize, and multiply by A to the 3 and normalize, and so forth, and compute this joint moment, it's 0. Okay, so here is a fun exercise, and every exercise that you see here, and definition will be used. It's like the gun in the play or something. So here is a nice way to generate freeness. So what do I mean? So say you have 2 random variables, A and B, like, I say random variables, but these are just abstract elements in the non-commutative probability space, and you like them. You like the marginal distribution of them. You just don't like how they behave together. They're not free. You want to make them free. It's like to construct the tensor product of 2 random variables that you do like. So it turns out that you can do that if you have like fresh bit of randomness, but bit here is a Haar unitary. So if you have a Haar unitary, that's what we said before, think of it as like a rotation, like something that's like really random, like a golden bit, in a sense. And it should be free from both of them. I define freeness of 2 random variables, but you can extend it to freeness of 1 random variable from 2 other random variables, generally for algebras. So if that happens, then it turns out that if you're going to conjugate one of them by U, then it's going to be free from B, from A, from the other one. So you can make freeness by conjugating by a Haar unitary. Okay? Keep that in mind. That's really, really important. It's a nice exercise, but the importance of it will be next time. Okay, I'm just going to slide it through. And now I think comes something which I was really happy to see, so I decided to show it, and hopefully there will be time, which is a central limit theorem for free probability, and at the same time for classical. At some point we have to diverge, but only at the end. And then I think that you will appreciate better why central limit theorem, why the square root of n appears there, and so forth, for combinatorial reasons rather than for, analytic reasons or so forth. Have you ever seen like a combinatorial proof of the central limit theorem? I mean, yeah, okay. So there is a yes and a no and quiet, but I don't think it's 50-50. I think, right. Okay, so let's see. So what is a central limit theorem, right? You kind of ask, say I have a random variable, many random variables, but they're all equidistributed. I'm looking at the most simple setting, and I'm centering them, and I'm just making sure the variance is 1. And I ask, what's the limit of this sum, right? And with hindsight, you know that you should normalize by square root of n, but don't worry about that. So you ask what happens like as you add up more and more independence, what happens, where do you approach to? And you all know the answer is the Gaussian, but that's what it is. Now, in this talk, as I said, or generally in free probability, you work with moments mostly. So by convergence, and there is a convergence here, what I really mean is convergent, like weak convergence, a form of weak convergence, which means that every moment converges. So it's a weak notion because I'm saying that for every m is going to be a moment, like the fifth moment, sixth moment, and so forth. If you are going to kind of consider your AIs or n increases and look at the f moment, at the end of the day it's going to be the mth moment of A. Right, yeah, I hope no one will look. Yeah, Ravi. So good. So technically they may live in different places and so forth. Right, but I just, yeah. Don't worry about that.
Does it mean they live in different places?
Yeah, they could live in different algebras sometimes.
And this is still well defined.
Yeah, exactly. And I just have erased it because it's not really critical for us. But yeah, you could have like they could only, I mean, this guy definitely live in a different place, possibly, because I don't know why A should live in where A1 lives and so forth, right? But yeah. Anyhow, so this is how it looks like. And let's prove the central limit theorem, okay? Like 3 slides prove the central limit theorem. And, forget about the square root of n. Let's fix m, fix capital N, but in my mind, capital N is like, it wants to go to infinity. We're kind of holding him, but m is finite and fixed. And I'm looking at, the nth power of this expression. That's what I care about. Divided by square root of n, it will come later. So if you think about it for a second, now it's non-commutative, so you need to be a little bit more careful. When you open this up, you just have to choose, from each of the m parentheses, which elements you take. So you can encode that as a function that tells you at the nth parenthesis, I take element number, something between 1 and n. So really, this thing is a sum of phis of AR1 up to ARM, where this is R. Encode the choice that you do. And now, the thing is, and that's the important observation, like the first one, is that if you are going to look, for example, at this moment in this sum, and that moment, even though the indices are different, the structure is the same. Like you have this and this are the same, like this and that, like the first and the fifth are the same. And same for the 2, 3, and 6 or something. And they are the same and so forth. So that should equal that because all of them have equal distribution. So you really don't care. If it doesn't change if I replaces the indices, it only depends on the partition that kind of encodes who's with whom.
The type.
The type. Let's call it type. Yeah.
But why? Could you say it?
Yeah, I assume that all the AIs are equal distributed.
No, you just assume something about the first 2 moments.
No, initially I I didn't maybe write it, that's true. But I'm loudly assuming that all the AIs are equally distributed. They have the same distribution. They're free or / independent, but they have the same distribution. So I didn't write it, but...
If there is another assumption, okay.
Yeah, there is, yeah.
Okay.
Yeah, otherwise it's... right. They all have to be the same.
So you're assuming AI?
Yeah, like they're all like plus minus 1 with probability 1/2. That's what I mean.
And they're free from each other?
Good. So so far I haven't used anything. So what I'm saying is that the only information you depend on R is for which indices are the same and which are not. So you can encode it as a partition. So for a partition, so think of a partition of M, right? We have M terms in every summit. So for a partition of M, let's call it V1 up to Vs. Okay, let's look at the example, for example. So these two summons correspond to this partition, right? In which 1 is with 5, and 2, 3, and 6 are together, and 4 is alone. I'm just saying that these are really, again, it's kind of isomorphic. These are just names. So phi of that is going to be phi of that. Because, well, actually, yeah, you are right, actually. You need to show that for freeness. You know that for the usual case, and you need to show that for freeness that's also the case, but that's expected. But you need to show that, you're right. Right? That's how it is. So now you can sum up it more cleverly. You can write this thing as summing over partitions of M. And then, there is this common value to all of the, R's that associated with that partition. Let's call it kappa pi. This is my kappa pi. And note that this value is, this value is independent of n, which is going to go to infinity in a second. It's a common value of this thing. It doesn't care about the indices, so it's just depend only on m, not on n, where the indices are coming from. And then you have this, which is how many R's are associated with that pi that we are considering at the moment. That does depend on n. That's not to the nth power, by the way, it's like something like this. But that does depend on n. And that's the only thing that depends on n. That doesn't depend on n, and also the number of sum n doesn't depend on n. Because it's just, you go over all partitions of m. M is 5. Okay, so here's a key observation, and that little observation is explained the square root of n. So if you have your, you take a moment like that, and say you have a singleton in your partition. So one element appears once. Then you know that in the classical case, you can factor it out, and we assume centeredness, so that's going to give you 0. And it turns out that even in freeness, that's an exercise. If that's A, B, and C, and B is free from the joint distribution of A and C, then you can factor it out. That's follow from the trivial, right? Yeah, right, good. Generally, you don't assume trivial, but right. Once you assume trivial, that follows.
You assume.
I'm assuming that, yeah, good. That's why I'm kind of not noticing. But you're right, because if you have A here, you can move that here and then use our AB. Good, very good. And so anyhow, in both cases, we still don't have to split the proof. In both cases, we get 0. So this means that all the partitions with a singleton vanish. And so all partitions in particular have size at most m over 2. Right, at least you have at least 2. This over 2 is the square root. This is what's going to happen.
What does it mean, size of partition?
Right, so this, for example, will kill the corresponding phi. The size of a partition the size of a part in the partition, sorry. The partition is of 1 to m, maybe I said partition instead of part. If in your partition there is a part of size 1, namely an element appears like with its unique index, then you're happy. I mean, he's sad, but I'm happy. He's dead. I'm left with less things to worry about. Good, so the number of parts in each partition is at most m over 2 because, pairing is the kind of biggest possible way of partition that. And so now let's do some calculation. So let's look at a pi to the n. That's, how many R's are associated with a partition. That's a very easy exercise. This. Okay, because, you choose who will sit in the first part and then who will sit in the second part, and you have pi parts. Which, pi is at most m, right? You partition m. It's actually at most at most m over 2 even. And n is going to go to infinity in a second, so let me write it as n to the pi, more or less. Okay, because it's roughly that. And so this limit that we cared about, and now I'm inserting the square root of n, because now I know what I'm kind of aiming against. Well, I just replace that with our nice sum. And I'm pushing here the limit all the way through the number of summons because it's independent of mn for kappa pi. So I get this expression. And from here you can see what's going to happen when I'm going to divide by square root of n to the m. Right? This is, I divided that. From here you can see what happens if pi is not of size m over 2. Right? It just goes to 0. Right? Because once pi is of size smaller than m over 2, strictly smaller, I mean, this won't save him. That's the function of m. It's not a function of n. That's amazing. So it would be n to the 1 minus m over 2. And as n goes to infinity, that goes to 0. Right? Unless m is 2. But generally speaking, the only pi's that survives are pairings. Right, so think about this for a second. So in this partition, so if I'm not giving you those, right, so if I look at this partition, I need to choose who will sit in entry 1 and 5. So here I chose 1 and here I chose 9.
No, that I understand.
Okay, yeah, I'm sure. Yeah.
Each one, that I understand.
Okay.
I don't understand, maybe I don't remember what a pi was.
It's the number of R's that associated with the given pi.
It is just a combination.
Right. It's without the fees
Okay,
or
it's
anything.
without the fees.
Yeah.
It's the coefficient.
Right. The kappa is the common value.
Okay, mix
Yeah.
the kappa and the a.
Right. Yeah. Good. Okay. Good. So that's interesting. That's going to be interesting now. But kappa is interesting. Yeah.
Okay. Great. That I understand.
Good. Yeah. I assume that. Okay. So good. So the only surviving pi's are pairings. That's that. We know that regardless classical free. And in the classical case, now we are going to diverge. In the classical case, for every pairing pi, you know exactly what is the phi of that, we're computing kappa now, what is the phi of that pairing, because you can just like commute things around. It will be phi of a, whatever I that was there squared, phi of a j squared. I and j will always be different, because these are pairings. Each of them is one per assumption, otherwise you get, the sigmas and so forth. And so really what you get is that the left-hand side, like this thing, what you care about, which is also that, is just the number of pairings of m, like times 1. And that's, that's kind of a similar exercise, m minus 1, m minus 3, and so forth. And these are the moments of, maybe you haven't never calculated them, but these are actually the moments of the distribution that you like. So it turns out that the analytic distribution that corresponds to these moments, when m is odd, of course, it's 0, because you can't do pairings, and when m is even, it's that number. You can do like integration by parts if you want, and you can show that this is the analytic distribution corresponding to these moments. So you prove with no integrals essentially, except for the last step, you prove the central limit theorem. Yeah, that's a good point. I didn't require that, I just said that, but it's enough that the decay will be fast enough. So let's do the free CLT now. So here, something interesting will come. So what are we doing? We're looking again at this expression. When we did classical CLTs, all of these were 1, so the question was count how many pairings you have, and we can all do that. But now we can ask, in the free world, where I can't use that because they don't commute, what can I say about this kappa pi? Some of them maybe disappear, I don't know what's going to happen. So let's see, let's just play with it a little bit, and we'll get the template. So let's say this is your pi. So, we usually draw it like that, like 1, 2, 3, 4. So 1 is with 2, 2 is with 4. So this means that here you have one random variable. I call it A instead of AI. And this is B instead of AJ, just so it will be easier to see. So the kappa corresponding to this pi is phi of A squared B squared, which we did already. And that's phi of A squared phi of B squared, which is 1. Right? We said that in this case there is no difference, which is 1. That's not interesting. But what about this one? So you see, this is another partition of 1 to 4 in this case, and now 1 is with 3 and 2 is with 4. So the corresponding kappa pi is this thing, but that's 0, because A and B are free and they're alternating like that, and they're centered by assumption. So phi of above is 0, so that pi doesn't contribute for some reason, and that will, because of triviality, as you said, for example. And you can kind of play with it, and then you can see what's the reason for something. First of all, it's going to be either 0 or 1. That's not obvious to begin with, but it is. And then secondly, it turns out that in order to survive, you must not have like a crossing pairing. Like a crossing pairing will eventually kind of pop up as you kind of open up these phis, and you'll see it, and it will end up looking at this calculation, and it will kill you. So it turns out, so I denote it like that. There is a definition here, but don't worry about it. A pairing is non-crossing if you don't have like two pairs that interlace in this sense, that cross. Yeah, good. So if you believe me, then the sum that we care about is how many pairings are non-crossing. Right, so the answer is the Catalan number. So it's an exercise. It is truly an exercise, just here. Okay. So the number of non-crossing pairings of 2m, it's not an exercise you should put, by the way, like I did it, and it's not a good idea. Don't put it in like the Bdida exam as part A, and then there's part B. And so don't do that. But it's,
you said don't do it, but I did it.
No, after, my experience, if there is one thing you should learn from this lecture, is don't do that. But anyhow, the number of non-crossing pairings of 2m is Cm. Like, it makes sense that the even one should be Cm. And then you can ask, okay, then what is the analytic distribution whose moments are the Catalan numbers? And that turns out to be the semicircular distribution. So this is the density distribution of it, but maybe you've seen it sometimes. It's like that's what happens when you take a random matrix with like symmetric random matrix with plus minus 1 entries and so forth. Look at the spectrum, it looks like this. Or if you take a d-regular graph, a random d-regular graph with d, which is increasing, it will kind of eventually will look like that and so forth. It's a limit object that appeared way before free probability. Right, so in 85, the date of the paper, but probably a journal and so forth. But I think a lot of hints were given from people that did statistical mechanics. They kind of started to see those things, and I think this Vokulescu guy was interested in von Neumann algebras and so forth, and Fourier groups. And he figured out that this appears in many places and abstracted in the right way. Yeah, and then Speicher gave it a kind of a more combinatorial treatment rather than analytic one, which is what you see here. Yeah, a whole world, very interesting one. Right, so but to sum up, free probability, and I put it on the top just to kind of, באופן בלתי מודע, to make you like, so free probability theory, it looks like this. Usually the densities are compact and nice, and it's this thing. Combinatorially, it kind of has something to do with non-crossings, not just non-crossing pairings, by the way. This is just when you compute CLTs, which is a very rough version of convergence, right? So, but non-crossing appears like the poset of non-crossing seems to be very, very much related to free probability, whereas the general poset seems to be, like of partitions, seems to be related to classical probability theory. Okay. So let me, in the remaining 10 minutes, to do this part at least. It's I think, the most interesting part. And then next time I'll do what I thought I'll do today. And then I'll know that I don't need to continue adding more slides for tomorrow's talk on the way back. But let's do the analytic perspective. That's the part I like most, really. Right. So I want to define something. It's, it looks technical, but actually it makes a lot of sense. So let me try to do it slowly. So if you have a distribution mu, and you should have in mind that we don't like to work with distributions. These are like Lebesgue measures, which you don't play with. Which they're just there, and you don't do much with them directly. But if you have a distribution like that, you can kind of associate it with an analytic, a function that you can work with and study that. So that's the good choice in free probability is doing the following, is considering what's called the Cauchy transform. So what is that? So technically it's just this thing. So you integrate 1 over z minus t, okay, against your density, your measure. But if you think about it for a second, I mean, we know how to do we know how to do these things, right? So it looks like this, and then you can expand this according to the geometric expansion and so forth. And you do that a little bit, like 2 lines, and you get to that. You get to this expression. So you sum over all really moments of your distribution, because you see t to the n appearing there, integrated against your measure, times 1 over z to the n plus 1. Don't worry about the plus 1. But if you look at it for a second, you say, oh, I know what's going on. So this analytic function encodes the moments when you Taylor expand around infinity, because you have 1 over z here. And a little shift, but right. So the picture you should have in mind, this is a function, it's a great function. It's an analytic function you can work with, and at infinity, it encodes the moments. Like once this converges, for example, if the distribution was compactly supported, once t is larger than the bound on the support of the distribution, this converges and everything's fine, and you can sum up infinitely many things and everything will be well, and that will give you a proper function. So the picture I have in mind, I'll go back to it in a second. So in free probability, you work here. You work in the skies with moments. This is like trademark, like no one calls it like that. But in free probability, you work with moments. And I really like this function, the Cauchy transform. You'll see why today and tomorrow. But you work with moments, and you can think of moments as expanding this function around infinity at the heavens, where this actually converges. But you also would want a way, so I mean, usually you start here, you compute the Cauchy transform, and then you want to get to the measure. You want to understand the measure. You want to go back to heaven. I'm assuming the measure is like real valued. That's why it's on the floor. And there is a way of doing that. It looks scary, but it's okay. It's called the Stieltjes inversion formula. And it tells you that if you only have like oracle access to the Cauchy transform, not to the measure itself, you can reconstruct the measure. Essentially, the measure of the open interval AB, unless you have some atoms, but don't worry about that, is what you have to do is you need to slightly get away from the real axis. So you see I have x plus I epsilon. I'm moving epsilon up a little bit. And I'm integrating the Cauchy transform, or its imaginary part, but never mind, over that interval. And then proper normalization and taking epsilon to 0, you get back the measure. But technically, there is a way. It's easy to work with. It looks weird, but it's easy to work with way of getting like the Cauchy transform allows you to like connect like moments and the measure. And it's actually not so trivial. I mean, if you have moments, then you have like a local view of the Cauchy transform around infinity. So who said that you can kind of get any information where the function as written like that is defined at all? So that's kind of the magic, if you're not used to it, it's a magic of analytic continuation, which allows you to do that. To say, well, if I understand the analytic function at some area, like open set or something like that, then I can understand it like in a much broader part of the complex plane and so forth. But there is this play that you do, which you work with moments, you go to the measure, you do something with the measure, you go back to the moments, and everything is through the Cauchy transform. That's how it behaves. You will see in an example. So the last thing I want to talk about is the additive free convolution. So that's the last thing I'm going to talk about, and tomorrow they are going to kind of come together. So let's see. So let's say you have two distributions, mu and nu, and you want to define a notion of additivity of these distributions, like convolution. But convolution, as you think about it, it kind of encodes independence in your mind. And I want to do it for freeness. Because, convolution means if they are independent, then what's the probability of getting a t? It's a z, z minus t, and so forth. So here is the recipe to do that, and it's non-trivial that all of these steps can be made to be done. So the first thing you do is you're going to algebraize. You're going to kind of realize those distributions with algebra, with elements. So we are going to construct an element A corresponding to mu and an element B corresponding to nu that encodes, if possible, that encodes in their moments the moments of the distribution. So, right, so you are going to set that A such that phi of A to the K is this phi, the Kth moment of mu. And same for B. And not only that, you're going to put them in, and it's not completely trivial, by the way, in the same non-commutative probability space and make sure, so the marginals will be like that, but A and B will be free. Okay, so you're going to do that. In standard probability theory, it's very easy, just the tensor product. But here it's slightly hairier, but okay, depending on your background, I guess. And then once you have A plus B, you know exactly how you should define mu plus nu. It should be that distribution that encodes the moments of A plus B, if exists. So to recap, you start with two measures, and you define algebraic elements that kind of encodes those measures, and you set them in such a place, like a non-commutative probability space, such that they are free. And now you can look at A plus B. And when you look at A plus B, maybe it has an analytic measure in the analytic sense. And that measure is going to be, and you need to prove uniqueness and so forth, but that measure is going to be the way you defined mu and nu. Okay? Yes?
Is A plus B even normal?
Right. So let's assume that A and B are normal, and then A plus B is going to be normal. Right. The one thing I want to stress about it is that this definition relies on freeness. I mean, that's how I constructed this. I mean, I constructed A and B which are free, and then look at the analytic distribution of that element. So if you have no freeness, you are left on your own to figure out how should you define that. And so in finite-dimensional operators, which is what's going to happen tomorrow, you need kind of, and again, a trademark, a freeness-free way of defining this thing. Okay? And that's going to be very interesting. But if you have freeness, it makes sense to define it like that. So the last thing I want to say is that having defined the Cauchy transform and this additive convolution, I can tell you that the master theorem here, it's a remarkable theorem. It underlies it is a ton of combinatorics, which is really nice, but I'm not talking about, but what does the theorem says? It says, the Cauchy transform is like moment. It codes the moment in a very straightforward way, right? So it turns out that's not the right way to do it. The right way is using what's called cumulants, which are like, you'll see in a second what I mean, and cumulants behave better under freeness. But, analytically, or even like formally as a formal sum, let's consider a K mu to be the inverse under composition in this ring of, power series of G mu. So K mu is going to be the inverse of G mu. So G mu of K mu is Z, which also implies that K mu of G mu is Z, by the way. So there is an inverse, trust me, because the leading coefficient is like 1 there, but there is an inverse. And that inverse, when you do that, when you go there, it's like Fourier, it's like doing the Fourier transform, but this is like the K transform. When you do that, now everything is clear. So you can ask, mu and nu. What can I say about the moments of mu plus nu in terms of mu and nu? I don't know. But if you ask me, what can I say about the cumulants, which are just the coefficients of this generating function, they just add up. So Q of mu plus nu of Z is just a sum, well, don't worry about that, a sum of Q mu and Q nu. This is just this is K of the 0. So you want that to be there. So it's just because I'm not normalizing, because I want to save you one more letter. But you see, when you look at it in the right transform, you can easily get the moments or cumulants of this new measure. Good. So I think I'll stop here, and tomorrow I'm going to kind of slightly repeat it and do I'm going to prove MSS, like the famous paper, but with a cheat. And that's not a proof, but that's good enough for tomorrow. We'll do more, but for starters, that's good enough. Okay, thank you.